Hello everybody, welcome to this short introduction to adaptive logics. I am Christian Straßer. Today I will take you on a logical journey to the land of adaptive logics. Adaptive logics have been developed by Diederik Bartens, and they are a type of non-monotonic logic, similarly to default logic, autoepistemic logic, logic programming, and many others. They provide a formally precise model of defeasible reasoning. For instance, if you look at the morning out of the window and you see wet streets, you will infer, because it explains the situation best, that it rained. However, later on you may learn that the streets have been cleaned and revise your inference. Similarly, in a murder case, our detective may infer to the best explanation that a certain person committed murder, just to change her opinion later on. If I tell you about a bird Tweety, you may infer that it can fly. If I tell you later that it is a penguin, you may revise your inference. Finally, if you look at a train schedule and you see a specific time when no train is listed, you will infer that no train goes at that time, but of course it could be that a train goes nevertheless. Similarly, with a restaurant menu, if a certain meal is not listed, it may still be served. Now all these examples were examples of defeasible reasoning, where a conclusion follows plausibly, likely, etc., but may be revised under certain conditions. Adaptive logics can be used to model the reasoning underlying all the three examples which we have seen. However, we will now look at inconsistency adaptive logics. They help us to reason with inconsistencies, like if you have several sources of information which contradict each other, a thick book of laws which is very complicated and may lead to inconsistent information, or a scientific theory which is inconsistent. In such cases, you want to block certain inference rules known from classical logic, which lead to disaster in the case inconsistencies or contradictions can be found in your information, such as the explosion principle or disjunctive syllogism. A logic that can be used for this purpose is the logic of paradox LP. It avoids the former two principles by employing a third truth value for inconsistency, I. Here it is the truth table for negation and for conjunction. However, this logic is quite weak, as it doesn't allow for disjunctive syllogism and other inference principles which you may want to employ in consistent circumstances. In adaptive logics, we make therefore a difference between the so-called lower limit logic, in which inference principles are collected, which are applicable also in inconsistent circumstances or sub-ideal circumstances, and the so-called upper limit logic, which is a stronger logic, but which has principles which are problematic in sub-ideal circumstances, that is, in circumstances in which contradictions occur. Our upper limit logic will be classical logic. The adaptive logic is somewhere situated in between the lower limit and the upper limit logic. It tries to apply the rules of the upper limit logic as much as possible. So for instance, disjunctive syllogism will be a rule of the upper limit logic but not of the lower limit logic, and the adaptive logic will apply it as much as possible. While the lower limit logic is a model of reasoning in subideal information states in which we have abnormalities, that is contradictions, the upper limit logic is a model of reasoning in ideal information states in which there are no contradictions or abnormalities. The adaptive logic adapts to the standards of the upper limit logic as much as possible by interpreting the information as consistent as possible. Now let us look at a simple example to understand how adaptive logics operate. We will look at a proof given this information, P or Q, S or T, not S, not P and S. What we do first is introduce the given premises. This is a good opportunity to explain the different parts of an adaptive proof. Each line of the proof consists of 4 columns. The first simply lists the line number, the second a formula, the third the justification, in this case the premise introduction rule, and the third a so-called adaptive condition. We will come to that in a second. Let us first introduce another premise. Now we introduce another formula by means of applying a rule from the lower limit logic. This is indicated by RU, which means rule unconditional. This rule is safe because it stems from the lower limit logic. In this case, it is simply the conjunction elimination rule, which is valid in the logic LP. In the next step, we will now apply a rule from the upper limit logic, namely disjunctive syllogism, to lines 1 and 3 in order to derive Q. This is labeled RC for rule conditional. Now this rule, as we can see, generates a non-empty condition, namely P and not P. So if you look at the lower limit logic, while disjunctive syllogism is not valid, a weaker form of disjunctive syllogism, which looks as follows, is valid. So from A, not A or B, we can derive B or A and not A, so or a contradiction. And this contradiction is moved in the adaptive proof in the so-called condition column. The line 4 therefore reads, Q is derived on the condition that there is no contradiction in P, because if there is no contradiction in P, even the lower limit logic would say yes, then Q is valid. So line 4 is a defeasible rule. It says Q under the defeasible condition P and not P. Now, if we can derive in this proof some information which casts doubt on this defeasible assumption, then we would have to retract this line. So in the fourth column are listed so-called abnormalities, which in our case are contradictions. At line 7 you can see another application of the rule conditional, and there should be a C rather than a RU, which derives again by disjunctive syllogism T, but again on the condition that a certain contradiction does not hold, in this case S and not S. Now at line 9 you see something interesting, namely S and not S is derivable on the empty condition, and this at this moment line 7 has to be retracted. It will therefore get marked in the proof. So this is the fifth element of an adaptive proof, namely the markings of lines. Sometimes lines will get marked, which indicates that these lines are at that very moment of the proof defeated, and therefore the formula at that line does not count as derived at that very moment at which it is marked. So note the mistake at line 7, this should be RC rather than RU. So let us look at the two types of rules in more detail. We start with the rule unconditional RU. So if you have in your proof lines L1 to Ln with formulas A1 to An on conditions delta 1 to delta n, and from A1 to An follows in the lower limit logic B, you are allowed to derive B with the rule unconditional. You just collect all the conditions you had on the previous lines. With the rule conditional, you have that from A1 to An follows in the lower limit logic B or a disjunction of abnormalities in delta. You collect all the abnormalities from before, from delta 1 to delta n, and you add the new abnormalities in delta to that line. The idea is that we assume that all the abnormalities in delta are false. Now let's look at some complications. So we're looking at a new premise set S. We introduce our premises again, we apply disjunctive syllogism on the condition here that there is no contradiction in P, introduce some other premises, and now at line 6 something interesting happens. We derive a disjunction of two abnormalities, two contradictions, one in P and one in S. Note that line 3 was derived on the assumption that there is no contradiction in P, but now we have the information that there is a contradiction in P or in S. Information, as in line 6, is called minimal DAP formula. It is a minimal disjunction of abnormalities, in our case contradictions. Now minimal DAP formulas motivate a first strategy of marking lines, the so-called reliability strategy, according to which a line L with the condition delta is marked at a stage S of the proof if and only if there is a minimal DAP formula over a set of abnormalities / contradictions theta for which theta intersection delta is non-empty. This is exactly what happens at line 3 in view of the minimal DAP formula at line 6. If we change our premise set a bit, add the premise S, then we can derive a shorter disjunction of abnormalities, namely just a contradiction in S, and our line is unmarked because line 6 is not anymore a minimal DAP formula. In the next example, we will motivate a different type of marking strategy. We will again derive Q by disjunctive syllogism, this time in two ways. In line 3 on the condition that the contradiction in P is false, and on line 6 on the condition that the contradiction in S is false. Now if we look at the minimal dub formula, there is exactly one which says either there's a contradiction in S or in P, line 8. Now according to reliability, both lines 3 and 6 have to be marked due to the minimal dub formula at line 8. But is this reasonable? Let's look at the interpretations, the LP models of the given information. We have, for instance, the following 5 models. The first 2 models have exactly one contradiction, the M1 in S, M2 in P. Now both of these most normal or consistent models make Q true, which motivates that in our adaptive proof Q should also be derivable. So we should devise a strategy under which it is derivable. For this we employ the technical notion of a choice or hitting set. So suppose you have disjunctions of abnormalities like here. You want from each disjunction at least one member. These are the choice sets over these disjunctions. And the minimal ones are called the minimal choice sets. In this case the first and the fourth one. In our example we have exactly one minimal dub formula. So we have 2 minimal choice sets, one consisting of the contradiction in S and the other one of the contradiction in P. So we can now define another marking strategy, the so-called minimal abnormality strategy, according to which a line L is not marked at a stage of the proof if we can find a minimal choice set at that very stage of the proof with which its condition has an empty intersection, like the red minimal choice set, the contradiction in S. And also, for every minimal choice set, we can find a line with the same formula, such that that minimal choice set has an empty intersection. So if you look at the yellow minimal choice set, we find another line, line 6, where the same formula Q is derived on a condition which has an empty intersection with that minimal choice set. Let us use a final example to demonstrate the minimal abnormality strategy once more. Here's a new premise set. We will now derive Q in 3 different ways conditionally. The minimal dub formulas will give us 2 minimal choice sets. If you look at line 7, you can see that conditions for it to be not marked according to minimal abnormality are fulfilled. There's a minimal choice set with which its condition has an empty intersection, and for each minimal choice set you will find another line where Q has been derived on a condition which has an empty intersection with that minimal choice set. Here are the minimal choice sets on the right hand side. So neither line 7, 8 or 9 are marked with according to minimal abnormality, but they are marked according to reliability. Here you see condition 1 and condition 2 of the marking definition in action. So we have already seen that markings of lines may come and go. That opens the question when a formula should be considered a consequence of the premise set. When is it finally derived? The definition of final derivability says that a line L with a formula A is finally derived in a proof if it is currently unmarked, and any extension of the proof in which the line may get marked can be further extended in such a way that the line is again unmarked. Then the formula is said to be finally derived. We will close this introduction to adaptive logics with some words on semantics. So if we look at the lower limit logic, it provides us with a semantics. It provides us with a set of models of a given premise set. These models, however, are not internally ordered. So it is not clear whether one model is more or less normal, provides a more or less normal interpretation than another one. And the adaptive logic now will provide an order among these models. It will order them according to how normal or how consistent in our application a interpretation provided by that model is. It says that one model M is more normal than a model M' in case its abnormal part, that is the abnormalities which are true in that model, is a subset of the abnormal part of M'. So looking back at our previous example, we had 5 models, and the abnormal part were inconsistencies in atoms. So if we compare our models now according to their abnormal parts, we will see that M5 is the most inconsistent and therefore the worst one, and the best ones are M1 and M2, which are not comparable with one another. So they are equally good according to this ordering. Now, the semantics which is adequate to the minimal abnormality strategy will exactly select the best models according to this ordering, in our case M1 and M2. And as you can see, in M1 and M2, Q is true and Q was also finally derivable. To make the connection between semantics and syntax or proof theory more concrete, we can define a consequence relation based on the notion of final derivability relative to a given strategy S, and a consequence relation defined in terms of the semantics. Now, in our case, minimal abnormality would say A is a consequence of S if and only if A is true in all minimal abnormal models. Now, these two consequence relations for minimal abnormality are exactly the same. So we have soundness and completeness, and similarly for reliability there exists a semantics such that the semantic consequence relation will be exactly the same as the one for the proof theory. And that's it for this short introduction into adaptive logics. I hope you had some fun watching the video. If you have questions, please write me an email. I hope to see you soon in person. Bye-bye.